Welcome everyone to the second video on statistical thermodynamics, and specifically the Boltzmann distribution function. Okay, so let's consider I have some container, some system, something where I have a bunch of molecules in that container, and these molecules can occupy a different set of energy levels. Now the energy levels themselves are discrete; they're at specific energies. And there's a spacing between those, okay? So it's not a continuous level, but discrete levels. And we'll see, right, when we talk about quantum mechanics in the next semester of physical chemistry, why we consider this, right? But let's consider, again, I have these discrete energy levels, okay? Energy levels, the lowest energy at 0, then at epsilon, then 2 epsilon, then 3 epsilon, so on and so forth, right? Okay. Right, now at any time, right, those molecules will have, right, some number of molecules in the energy level 1, some number of molecules at energy level 2, some level of molecules at energy level 3, so on and so forth. And we'll talk about that configuration, that distribution of molecules in different energy levels as a configuration, right? So this notation here is, right, saying I have N1 molecules and epsilon 1, N2, and epsilon 2, N3, and epsilon 3, so on and so forth, right? Right, and so yeah, that's right a configuration in the system. Let's assume, right, that right the molecules are not interacting, so that the total energy is just a sum of the number of molecules in a given energy level times that energy, okay? Right, so just summing up the energy of all the molecules, right, so that they aren't, there's no extra energy term, right, dealing with, like, you know, molecules I and molecules J and some epsilon ij or something like that, right? There's no interaction energy term, right? The energy of these molecules is just based off of what energy level they're occupying, right? And then we're going to assume, right, that no specific energy level is more likely to occur than another, right? That it's not more likely to be in 0 or epsilon or 2 epsilon or 3 epsilon energy level, right? That there's nothing making either of these energy levels more desirable, right, if you will, okay? There's no attractive energy between the energy levels, right, or things like that, okay? Right, and so that means that each energy level has an equal weight, okay? Right, and then what we're also going to assume, right, is not just, again, that the total energy is the sum of all the particle energies, right, and that, right, that each level has identical weights, right? We also want to think about the fact, right, that there is some total energy, right, that I'm going to assume that my molecules have some maximum total energy, right? Right, but given that maximum total energy, right, there's many different configurations I could consider, right? Right, there might be a situation, right, where I take 5 molecules away from energy level 1, I put them in energy level 2 and energy level 3, right? And I potentially have kind of the same energy, right, in my total system, okay? And so there's different types of ways you can organize the molecules in these energy levels that have some total energy, right? Okay, and the weight, the chance of having that, say, total energy and having a specific configuration, right, is given here, right? So this is the weight of a given configuration, right? So a given set of n's, right? N1, N2, N3, right? That given set of occupations and the energy levels has some weight, right? Some total number of ways I can occupy those energy levels, right? That's what this is, right? This is the total number of ways I can occupy those energy levels, right? So this weight is a number that's typically much greater than 1, right? And so, right, and so the question we can ask then, right, is given all of this, what's the probability, given some, say, total energy, that I'll have, right, that what my molecules will be in a specific energy level, right? And so, right, the probability, again, is related with the number of ways that outcome can happen, divided by the total number of outcomes, okay? Right, and so to kind of solve for this, right, what we're interested in then, right, is, again, this weight gives us the likelihood of being in a certain outcome, right, that weight with that factorial, okay? And so what I want to consider, right, is if I potentially change the occupation of a specific energy level, how does that change the weight? And then find what is the largest weight, right? Because the largest weight means the largest frequency of outcomes, right? Right. So the largest weight for a coin flip, right? If I flip the coin 4 times, right, the largest weighted outcome would be 2 heads, 2 tails, right? And so, and that's going to be related with the most probable outcome, right? And so what I'm interested in is finding how that weight changes with an occupation in a specific outcome, right? So derivative of the weight, respect to derivative number of, a specific occupation within an energy level, okay? And when I set that equal 0, right, that will find the maximum or the minimum of this weight function, right, W. And we're interested in what's the maximum, right? Now, solving this derivative is a little bit more annoying than if you look at the natural log of the weight, okay? And so that's what we're going to do, right? But the maximum position of the weight still is the same as the maximum position of the natural log of the weight, okay? So those will have the same maximum, right? And then again, well, I'm going to do this derivative, but I want to keep the fact that, right, when I'm changing the number of particles in the ith state, okay, that is not changing, right, that's not changing anything with respect to the total number of particles, right? So if I remove some particles from the nth state, I got to put them in the jth state, right? And then again, that my total energy, if I move the particles around from one energy to another, that total energy stays the same, right? So I got these 2 constraints, okay, in this optimization, right? So I want to find what is the maximum likelihood occupation of my molecules in these energy levels, assuming some total constant energy and some total number of particles, okay? Right? Well, when you solve that math, take that derivative, simplify things down, apply those constraints, you will get the following answer here, okay? That most likely outcome, okay, and the probability of that most likely outcome, so P epsilon I, right, right, is related with the exponential of minus beta divided by, or times epsilon I divided by sum over j e to the minus beta epsilon j, okay, which is going to be simplified down as calling Q, this partition function I'll talk more about in future videos, okay, right, and so that is related with the most likely outcome. And this distribution, this probability distribution, is called the Boltzmann distribution, okay? So again, this probability distribution uses the assumption that you have some total energy, right, that is conserved, right, and total number of particles that's conserved, and that the likelihood of your particles occupying one level versus another is unchanged, right, and that they're not interacting, okay? Right, and so what is the beta in this function, right? So again, the probability distribution, okay, P sub I, right, which is the probability of being in energy level I, is exponential of minus beta epsilon sub I over Q, this partition function, okay. Beta itself is going to be equal to 1 over KT, okay, where K is the Boltzmann constant, and T is your temperature. Okay, and if I'm curious about what is the probability of being in state I versus the probability of being in state J, that's equal to this ratio, okay, which ends up being just e to the minus beta times the difference between those two energy levels. Okay, right. And again, this is the Boltzmann distribution function, okay, that we're talking about here. Okay, again, it works for any system where you have a bunch of different energy levels and a bunch of different particles that can, occupy those potential different energy levels, right? And it's related with the energy of those levels, right? As well as in this partition function Q that we'll talk more about in the subsequent video. Okay. One thing to note here, we didn't consider kind of degeneracy, right? That having two energy levels or two levels that have the same energy, right? Okay, like this, right? So in this situation, okay, the Boltzmann distribution function just gets modified by these factors G sub I, okay, where G sub I is equal to the degeneracy, right? Right, so if everything's singly degenerate, G sub I is equal to 1. If it's doubly degenerate, G sub I equals 2. Triply degenerate, G sub I equals 3, so on and so forth. Okay, so that's how you include the degeneracy. You just multiply by the number of states that happen to have that same energy. Okay. So let's consider with this Boltzmann distribution what the distribution of, say, particles look like in this system at certain instances, right? So let's first consider the case where temperature is approaching 0, right? Well, in the case when temperature is approaching 0, everything is going to be occupying the lowest energy, okay? And you can get that from the probability of state I, okay, over the probability of state J, right? That this goes to 0 for everything essentially where I is greater than J. Okay. And so the energy flows downhill to the lowest energy state, right? And the same thing as delta G equals delta H minus T delta S, right? As temperature goes to 0, right? That stuff doesn't matter, right? Your lowest free energy state is related with the lowest enthalpy state, okay? So you're going to favor, right, whatever state, whatever possibility, whatever outcome has the lowest energy. Right. Now, if we think of temperature going off to infinity, right, having an infinitely large temperature, okay, that's going to end up having a probability of everything equally occupied over all states, right? Because again, we stated from the beginning that there is nothing that says one state is more likely to be occupied than the other, except for the fact that if I have a total energy, right, I can't have my particles in some extremely high energy level, right? Where my energy of the system exceeds that of the defined total energy, right? So as temperature goes to infinity, right, the total energy within the system, okay, related to temperature is going to go to infinity, right? So you're going to have infinite amount of energy, right? And if the infinite amount of energy, all particles will try to spread out into all different states. So that's the most likely outcome, okay? And that is, again, in your, say, delta G equaling delta H minus T delta S, right? That's when your T delta S term dominates, right? That's when entropy dominates, right? And we talk about, when we introduce entropy, we talk about entropy S is equal to ln Q, okay? Q is the partition function we have just been talking about, and we'll talk more about in the next video, okay? And so Q, right, is directly related with the distribution of states, right, which is what entropy is related with, right? Entropy is related with disorder, with things being spread out as much as possible, right? Because entropy is just essentially a measure of the statistics of your situation, right? Of what is the most probable outcome, right? Is related with the most highest entropy thing, right? Okay. And so, right, in general, as temperature increases, right, your distribution gets from more localized in the lowest energy states, starting to get more and more spread out to higher and higher energy states.